In this video, we are going to continue our discussion on the different laws of probability, and we are going to begin with conditional probabilities. All right, so conditional probability is obviously a type of probability, and it is the probability that one event will occur given that some other event has occurred. All right, so when we are looking at these conditional probabilities, right, again, we're saying something has already happened, right? Some event has already happened. Given that we know this, right, given that this event has already happened, what's the probability that something else also happened? That is essentially what we are asking here. All right, and this brings us to our ninth law of probability. All right, so the probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B. All right, so this is how we notate it. We've got our P, that's our probability statement. We open that bracket, right, and then the actual event is A line B, right? And so you'll read that A, then the line is given, or so A given B, right? So A is what we're kind of really interested in. B is what we're saying, this is what's given, this is what's already happened, right? B's already occurred, we know that, all right? And then we're going to calculate this probability as the probability of the intersection of A and B divided by the probability of B. All right, so let's take a look at an example of calculating a conditional probability. All right, let's say that we'll do just kind of some shorthand here. We'll say A is even and B is spade. Those are our events. So A is even numbered cards and B are the spades. So that suit of cards. So if we are looking for the, let's see, which one did I do first? That's it, okay. Oh yeah, that one makes sense. All right, so let's say that we were looking for the probability of drawing an even card given that we've drawn a spade. All right, and so that's exactly what we're doing here, right? We're saying I've got a deck of cards, right? You know, I draw one, I look at it, I look at you guys, and I say, this card is a spade, all right? What's the probability that is also even? All right, that's kind of what we're trying to do here. All right, so when we do, right, there are a couple of ways for us to do it. All right, so one, let's just set up our calculation. So in the numerator, right, we need to have the probability of the intersection of A and B. All right, and so to find the probability of an intersection, we think how many outcomes are in this event, right? So how many even spades are there, right? Well, there are 5 even cards for each suit, right? So there are 5 even spades. Right? And then we would divide that by the number of outcomes in the sample space, which is 52. Then for the denominator, that's just the probability of drawing a spade, what is given. All right, we know that there are 13 cards in each suit. All right, so the probability of drawing a spade is 13 over 52. All right, now you can just go ahead and run through this calculation as it is. All right, but we might also notice that we can simply cross out these kind of denominators, right? So are divided by 52, right? Those are going to cancel out, leaving us 5 over 13. And that's going to give us a probability of 0.385. So when we're doing a conditional probability, and I'll go ahead and tell you that we're going to talk more about this later on in a different video, but really all we're doing is we're just shrinking the sample space, right? So instead of looking at the entire sample space for whatever the experiment is, we're only going to be looking at what's given, right? And essentially what's given becomes our sample space, right? Because in this example, even given spade, right? Well, I can just, any card that's not a spade, I can just toss out because I don't care about it at this point, right? Because I know it's not one of those cards. I know I've been told that it's a spade, so I only need to look at those 13 spades, right? And then when we go to say, well, how many even cards are there? It's like, well, we know that there are 5 even spades, right? We're gonna look at something in a different video that hopefully makes that concept a little bit clearer. I think it'll actually be the next video that we'll look at that, as well as look at a bunch of different examples of all of the other kinds of stuff we've done. All right, but that is our conditional probability. All right, the next thing that we're going to talk about in this video, and really the last thing, is independence, the idea of independence. All right, so I'm going to give you guys the kind of the short version of this, just so we can kind of put it all up here as quickly as possible. All right, independence means, right, if two events are independent, it means that the occurrence of one does not change the likelihood of the other one, right? So the one of the events occurring doesn't change the probability of the other one occurring, right? That's essentially all we're saying, right? And that's what we're going to be putting up here in just a second, right? But again, it just means they don't affect one another, right? It's kind of like they're not related. They're not going to you know, one happening doesn't make the other one more or less likely to occur. All right. Another, just a quick, before we actually get into the whole thing, a lot of students tend to confuse independence and mutual exclusivity. All right, they are not the same thing. All right. In fact, if let's see, which way does it go? If they are mutually exclusive, then they cannot be independent. All right, just by definition. All right, so I guess it would work both ways. If it's independent, it can't be mutually exclusive. Okay, so, but that is what independence is. So now let's write this down a little bit mathematically. All right, so if for events, all right, actually that's not how we want to phrase that. Let's say events A and B are independent if and only if, that's what the little if with 3, or not with 3, with 2, the if with 2 f's. All right, so if and, actually let's just write that out. We're never going to use that again. We don't really need to introduce that just for this. All right, so if and only if the probability of A given B equals the probability of A and the probability of B given A equals the probability of B. All right, so this is essentially just saying in kind of mathematical notation the exact same thing I said earlier. All right, if the probability of A, given that B has occurred, is equal to the probability of A, that means that it doesn't matter whether or not B occurs. The probability of A occurring stays the same. All right, the same is true for the second condition. All right, if the probability of B given A is equal to the probability of B, that means that it doesn't matter whether or not A has occurred, the probability of B occurring is the same. All right, that is what it means for two events to be independent. All right, importantly, both of those conditions have to be met. All right, so if you're working through a problem and whichever ones you pick first to do this thing with, all right, if the probability, the conditional probability equals the normal one, that's great, but you're not done yet. You have to go and do the second one. All right, you have to check both of these. All right, now the flip side of that is if the first one you do, if they're not equal, then you can stop right there and say that they are not independent, right? All right, so let's do a quick example of this. All right, so we're going to stick with kind of even and spade. All right, and so what we would be asking, all right, or if this was on a homework or a test or something along those lines, right, the question you would be asked is something like, so kind of a weird way to phrase that. Is drawing an even card independent from drawing a spade, right? That might be how it's phrased, right? But it'll ask explicitly, are these independent, right? So are even and spade independent of one another, right? Some way, something along those lines. All right, so when we go to do this, all right, probably the first thing that you want to do is you just pick which one you want to start with. Let's start with even, just because it's A. And so we're going to need to know the probability of even. And so, of course, even, right, there are, well, I'll just tell you, there are 20 total, right? There are 5 even cards for each suit, right? So with 4 suits, that's a total of 20 even cards. All right, that's going to give us a probability of 0.385. Then we've already calculated the conditional probability of even given spade, right? That was the last example we did. And we found that to be 5 over 13, which also gave us 0.385. All right, so this is a good start. Our first condition has been met. So the probability of even equals the probability of even given spade, right? Those are both 0.385, right? But again, just because that first one has been kind of met doesn't mean we can stop there, right? We have to keep going. We have to check the next one, all right? So we're going to need to know the probability of drawing a spade. All right, so once again, there are 13 cards in each suit. 13 over 52 is 0.25. All right, we could have probably also just known that off the top of our heads if we know about cards a little bit, because there are 4 decks, or 4 suits in a deck, and there's an even number in both of those. All right. Then we're going to look for the probability of spade given even. All right, so when we are doing this, the numerator is going to be the same because it's it is the intersection of spade and even. So when we did it over here and when we're doing it here, it's going to be 5 divided by 52. All right, then our numerator, our denominator will be different because now it's the probability of even. All right, so, well, luckily we've got this up here. All right, so we've got 5 divided by 52 divided by 20 divided by 52. All right, once again, those kind of divide by 52s, those can be canceled out. We're left with 5 over 20, and that is 0.25. All right, so the probability of even equals the probability of even given spade, and the probability of spade equals the probability of spade given even, right, both at 0.25. So in this example, all right, these would be independent. All right, and actually in this case, we might, if we kind of as we get more familiar with kind of these probabilities, right, we probably could have just looked at this one and said those are going to be independent, right? There's no reason why drawing an even card is going to change the probability that it's a spade, right? There's no reason for those to affect each other, right? Some things you can do that with, especially the kind of simple experiments like flipping a coin, rolling a die, stuff like that. But for most of the other things, especially what we're going to do probably in the next video, you actually have to check, right? You can't just say they look independent to me, or say there's no reason that they would not be independent. All right, but that is independence. That's how we would check for independence. Now the very last thing that is related to independence, and this is our 10th law of probability, so we're going to be done with those after this. All right, so if events A and B are independent, then we can calculate the probability of the intersection of A and B by multiplying the probability of A times the probability of B. All right, and this is expandable. All right, so if we have n events, actually, let's just say, shorten this, yeah. So let's just say if we have n events, A1, A2, all the way to AN. All right, so if those n events are independent, then we can calculate the probability of the intersection of those n events by multiplying their probabilities. All right, so that kind of got a little cluttered there at the end, but right, really this part is just an expansion of this top part, right? I would say this is the one that probably is going to make the most sense, but again, this is just expanding it out, right? Just getting more and more events, right? So as long as all of those events are independent, if we want to find the probability of the intersection, we can just multiply their individual, the probability of the events occurring. All right, but that is the 10th law of probability. All right, so in the next video, what we're going to look at is something called a joint distribution table. And we're going to use this joint distribution table to answer kind of, we'll just do a quick overview of what it is, and then we're going to actually run through, I think, an example of almost everything that we've done so far. All right, so that video might end up being a little bit longer, but it will be full of examples. All right, but that's it for this video, and I'll see you in the next one.